Now we will use expression for electric potential due to a point charge for determining electric potential due to an electric dipole. Electric potential due to dipole can be determined at axial or equatorial or at arbitrary position. First, at axial position, if we have to find electric potential due to dipole at axial position, then say here is a point X on the axis of dipole, distant r from its center. Electric potential at X due to dipole means electric potential at X due to negative charge plus electric potential at X due to positive charge. Now we know that electric potential is a scalar quantity, so electric potentials due to positive and negative charges will be added directly to get the electric potential due to dipole at point X. We know that electric potential due to negative charge will be negative, while that due to positive charge will be positive. If electric potential due to minus Q at the position of X, say V negative, will be 1 over 4 pi epsilon Q, and this time charge is negative, so potential will be negative. Charge upon distance, and distance of minus Q from X will be R plus L, so R plus L. Similarly, electric potential due to plus Q at point X, say V positive, that will be 1 over 4 pi epsilon Q upon distance, and distance of X from plus Q will be R minus L. Now electric potential due to dipole at X due to electric dipole, V will be V positive plus V negative. This is equal to 1 over 4 pi epsilon Q upon R minus L minus 1 over 4 pi epsilon Q upon R plus L. This is equal to LCM will be R square minus L square, and Q upon 4 pi epsilon will be taken outside. So we will have R square minus L square as LCM, and here R plus L minus R minus L. So R plus L minus R minus L. This will give V is equal to Q upon 4 pi epsilon R plus L minus R plus L. So plus R minus R will get cancelled, and plus L 2L. So into 2L upon R square minus L square. But Q into 2L is electric dipole moment P. So it will give V is equal to 1 over 4 pi epsilon P upon R square minus L square. If dipole is small, that is L less than R, then L square will be neglected as compared to R square. So electric potential at axial position will be 1 over 4 pi epsilon P upon R square. Now next thing is electric potential due to dipole at equatorial or broadside on position. For equatorial position, the distance of point X from each of these two charges will be same. Also the magnitudes of the charges are same but of opposite nature. Hence the potentials due to these two charges at point X will be equal and opposite. Hence the total potential at point X will be 0. that is electric potential at X due to dipole V will be V positive plus V negative, that is potential due to positive charge plus potential due to negative charge. But potential due to negative charge will be negative, so we will get 1 over 4 pi epsilon q upon, this time the distance of X from these charges will be under root r square plus L square. So distance under root r square plus L square, and potential due to negative charge will be negative, and magnitude of this electric potential will be 1 over 4 pi epsilon q upon under root distance, that is r square plus L square. This gives the total electric potential V is equal to 0. Thus, if point P lies in equatorial plane, means this plane, anywhere the point can be. If point X lies in equatorial plane of the dipole, then electric potential at that point will be 0. Now we will find electric potential due to dipole at an arbitrary position X. For this arbitrary position X, we have the polar coordinates with respect to point C. The distance of X from point C is R, and that is making an angle theta with the direction of electric dipole moment of the dipole. To determine electric potential at X due to dipole, we will have to determine electric potential at X due to minus Q as well as electric potential at X due to plus Q. And for that, we will be requiring the distance of X from minus Q and distance of X from plus Q. And for those distances, we will draw perpendicular from B on CX. And after drawing this perpendicular, say BN, we will assume that the distance BX is equal to the distance XN. That is, BX is equal to NX, and NX can be taken as CX minus CN. Now Cn can be obtained using trigonometry, and according to trigonometry, for angle theta, Bn will be perpendicular, Cn will be base, and BC will be hypotenuse. So cos theta is equal to base upon hypotenuse, that is Cx, that is R minus Cn, yani base is equal to hypotenuse into cos theta, means L cos theta. Similarly, distance of minus Q from X can be obtained by drawing a normal from the position of minus Q over XC produced, and say this time the foot of the normal is M. Then we can say that AX is equal to MX. But how to find MX? Again we will use this angle, vertically opposite angle, as theta. So using vertically opposite angle theta, we get AX is equal to MX is equal to CX plus CM. This is equal to CX is R plus CM, again base for angle theta in triangle AMC, and base is equal to hypotenuse into cos theta. that is L cos theta. Now we have the distance of x from minus q as well as from plus q, and hence electric potential due to dipole at x, V will be electric potential due to positive charge plus electric potential due to negative charge, and this will be equal to electric potential due to positive charge will be positive, while that due to negative charge it will be negative. So 1 over 4 pi epsilon q upon distance, and distance of x from positive charge is bx minus 1 over 4 pi epsilon into q upon distance of negative charge from x, that is ax. This implies V is equal to q upon 4 pi epsilon will be taken outside, and we will get 1 upon bx, that is 1 upon r minus L cos theta minus 1 upon r plus L cos theta. This is equal to q upon 4 pi epsilon as such, and LCM of r minus L cos theta and r plus L cos theta, r square minus L square cos square theta, and this will give r plus L cos theta minus r minus L cos theta, that is minus r plus L cos theta. This gives V is equal to q upon 4 pi epsilon into r will be cancelled with r, L cos theta 2L cos theta upon r square minus L square cos square theta. This implies V is equal to 12 into q will give P, so 1 over 4 pi epsilon P cos theta upon r square minus L square cos square theta. Now for axial position, theta is equal to 0 degree, so V is equal to 1 over 4 pi epsilon cos 0 is 1, so P upon again cos square 0 1 r square minus L square, and for equatorial position theta is equal to 90 degree and cos 90 degree is equal to 0, so V is equal to 0. Cos 90 will make V as 0. Thus, it is the general expression for electric potential due to an electric dipole. Now, we will establish relation between electric field and electric potential. So here is a uniform electric field E in which a positive test charge Q naught is placed. This electric field will exert a force F equal to Q naught E on this test charge in its own direction, and if we are displacing the charge Q naught through a distance dr against this force, then the work done on Q naught dw will be F dot dr. Dr will be the displacement vector of charge Q naught, and its direction will be from initial position to final position, that is this way. It shows angle between direction of force and direction of displacement vector is 180 degree. Hence, work done dW will be F dr cos 180 degree. We know cos 180 degree is -1. So this is equal to minus value of F, magnitude of charge multiplied by magnitude of electric field, that is Q naught into E and into dr. This implies dW upon Q naught is equal to minus E into dr. This expression shows that dW upon Q naught is work done in moving unit test charge from one point to another. Hence, dW by Q naught must be electric potential difference between the positions separated by distance dr. So dW by Q naught is equal to dV, that is electric potential difference across two positions separated by distance dr. So we get dV is equal to minus E dr. This expression can be used either to determine electric potential or potential difference when electric field is given to us, or to determine electric field when electric potential is given to us. This shows, number one, electric field E is equal to minus dV by dr. Here dV by dr is electric potential difference per unit distance and is called potential gradient. Thus, electric field is equal to negative of electric potential gradient. Thus, if electric potential is known to us, then by differentiating expression for electric potential with distance r, we can get electric field. Similarly, again from this expression, V is equal to integral 0 to V dV. This is equal to minus integral E dr, and if r is changing from r1 to r2, then it will give us electric potential difference across two positions represented by r1 and r2. Thus, by integrating electric field with distance r, we can get electric potential or electric potential difference. We can use these two expressions. Say we know that electric potential due to a point charge V is 1 over 4 pi epsilon Q by R. From this expression, we can find out electric field due to a point charge. And if we are using this expression, then electric field due to point charge will be minus d by dr of V, that is 1 over 4 pi epsilon Q by R. And this gives E is equal to Q upon 4 pi epsilon outside the differentiation and d by dr of r to the power minus 1. And differentiation of r to the power minus 1 will be minus 1 upon r square minus q by 4 pi epsilon d by dr of r to the power minus 1 r की power minus 1, that is minus 1 upon r square. This minus multiplied by minus will become positive, so E will be 1 over 4 pi epsilon q upon r square. Similarly, by integrating this expression with distance r, we can find out electric potential using the expression of electric field. If you think this video is of any help for you, then please share it with your friends so that they may also be benefited by it.